Hi everyone and welcome to this video. So today we are going to finalize our series on logistic regression with a video episode on discussing an example in how to implement logistic regression in Python. So we've had two episodes before where we first discussed the concept of logistic regression, explaining how we can be able to model the relationship between various predictor variables to a binary response, yes or no. For example, defaulting on a loan, yes or no, a customer churn, yes or no, or even outcome experiencing a disease, yes or no. So our equation for the logistic regression, we say that we'll be modeling the log probability of an event happening, because now given that our response is binary, it's coming from a binary distribution. Make sure to check out our first video on logistic regression to have an in-depth understanding of that. We went ahead again and just did an example in R, which will be doing the same today here at the same data set. And our data set comes from a study in the United States where 100,000 individuals were enrolled, and a couple of variables, health and demographic variables, were collected, and a link to this dataset is attached in this Jupyter notebook file, which you can find in the description and also in my GitHub repository. So our goal for today will be just to fit and see how this set of predictors associate with the response variable, yes or no. So I won't go into the detail of the data analysis, but this is just as a nutshell of the variables that we have. We had the year, which was a distribution between 2015 to 2022, then the gender, age, location, the state which they are coming from, then their race, and we also had hypertension, heart disease, whether they smoked, yes or no, their BMI, and then their HbA1c level, their glucose, and their diabetes, and also whether they had diabetes, yes or no, and then finally the clinical notes. So these are the list of the variables that I've just gone through. So what we're going to do initially, I won't go through the EDA, but in a nutshell, in summary, what we want to do, we want to just extract the variables that we're interested in, and then of course we'll collapse all of these. We'll collapse all of these race variables into one, so that we just have one variable. And then of course we'll drop variables that we're not interested in, for example the location and so forth. So in the EDA, we also explored some of the characteristics of the data, like they don't have missing variables. We also saw how we were able to just wrangle the data and see their distribution. And then also we saw some visualizations that you can find in the dataset. We also created some new variables, such as the BMI category, which is just a category based on the BMI categories that we have from CDC and WHO, underweight to severe obesity. So we felt that instead of just using the numeric BMI, it's important to use these categories which are more familiar with and we interact with on a daily basis. So in a nutshell, our distribution of the Y variable, we saw that we have 8.5 in our previous example. Still the same data, so we have 8.5% being diabetic and 91.5% being non-diabetic. Our data is highly skewed, very biased, but that's not the work for today. We just want to focus on how do we implement this in R. So some couple of more visualization that you'll be able to see in the notebook. So in order to go further, I'll just rerun the first above cells so that we can have moving together. But this is the description of the variables that we have. We see we have year being an integer. We also have a couple of object variables. And remember from my video in logistic regression, linear regression, we saw that unlike in R where we could just add these object variables, the categorical variables, into the model, Python won't be able to handle that, so we need to encode them. So that will be one of the first tasks. We'll also drop the variables that I mentioned that we won't be having more importance of them. I already dropped the clinical notes column, so that we just strictly remain with those that we need. So this is what we have. If you see, we've been able to drop the year and the BMI because now we have the BMI category. Also, you can see now, based on the categorical variables, you can see the distribution, like female, male. You can see also the smoking history, and also you can see how we were able to group the variable of the race. Some other couple of more here we can see in the text editor, the BMI category and so forth. So the first task now will be now to encode the variable. So we are going to use ordinal encoder, and I mentioned in a previous video that although we did it manually, we can be able to do it automatically. So to do this, we are going to import pandas as PD. Of course, I had already imported this, so there's no need for this. But you can, from sklearn.preprocessing, so these are a couple of preprocessing that we need in order to make our data sets completely numeric. We'll be importing ordinal encoder. We'll also, from sklearn.compose, we'll import the column transformer, which will just enable us now to transform these columns that we want to encode. So the first step is now to list these columns that are categorical. So we have gender, the race, smoking history, and BMI category. Now we create them into a list. So that's what we do here. Then next, we just now used from expand on column transformer, and we have to give it what are the transformers. So we say it's ordinal because our data is categorical. Then of course we call on the ordinal encoder. We won't pass any functions in it, but after that we'll just give the list of our variables that we are interested in encoding. Then of course, what about the variables that are not in the data set? What do you do about them? So we just ask them to ignore, pass through them. And then now you just fit. So preprocessor.fit transform, use now passing your data, your data. So this, we created a preprocessor, we instantiated a column transformer. Then now we just fit it, we fit and transform diabetes. Then of course, we'll extract the columns that we were interested in, and then of course just convert it to a data frame. So when we run this section, we see finally everything is now a float, which is what we want. The next thing now, I just wanted to extract how it's been encoded, so that it can be very important for us when we will be interpreting. So like from here, in order to do this, I just created a code loop, and this will just go back to what we've created, this preprocessor, how we were defining it, so that we just want to go and see how was it able to now encode into numeric, so that we know what does 1 represent, what does 2 represent, or 1, 0, so forth. So this is what we have. We print it, looping through the list that we created the columns to encode, and now just give us the categories. So we see like male has been encoded to 1, female to 0. Then under race, African American is 0, Asian is 1, Caucasian is 2, other is 4. Of course, and for normal, obese, overweight, and so forth. That's what we have there. Then you can do it manually, yeah, like we did it before, but this is just a simpler way to do it. So now into the model building, we need to import some packages that we need. So from sklearn.model selection, we import train test split, and this will just allow us to split our data into train and test. We'll also import logistic regression from sklearn linear model to help us now to instantiate the model and fit the model. Then in order to see how our model performs, we now use the metrics. So from sklearn.metrics, import classification report, the confusion matrix, and the accuracy score. So these are the three packages, libraries that we're importing here. The next step is now to split our data into train and test. So in Python, how do we do this? We first create a list. We now first create a data set of X, then a data set of Y. So how do we do that? So we just go to the main, bring our encoded data set, then we drop the Y variable so that you can only remain with X. When dropping, remember to set axis equals to 1, so that at least Python understands that we are dealing with the columns. Next, how do you extract now the Y variable? You just now take your data set and just extract the column that you're interested in, which was diabetes. Then to split the data into train and test split, what we'll do here, we'll now remember we imported train test split, so you can go to train test split. Then once you open the bracket, if you're using Jupyter Notebook, you can open the bracket and just press Shift Tab to open the docstring, you can be able to go and see we have the example of how it's been explained. So we have the train test split. You can just copy this ahead, adjust how it is from here, X train, Y X test, and just like that, and then just delete this section so that you can have it in one line. So X train, Y train, X test, and that. So what it takes the X variable, then the Y variable, then it will now allocate. Then the test size, so for us we are splitting into 70 and 30, then choose a random state. So in order to have the exact results with me, ensure you choose 42. The next step now, it's just to instantiate the model. So we just say, we call our model diabetes model, then we take it, we call logistic regression. Then it takes in a couple of functions, but for some of them, like the random state and of course the solver is very important when you want to optimize your model. By default, the LBFGS is used, but you can also use any, depending on how you want and depending on how you understand your data. The most important thing is to choose the max iteration. I went with 1,000, but you can choose 100, which is the default, or any number. But if important to note, when you do not fit, it will pass a warning that telling you that the LBFGS failed to converge. So like it doesn't know the number of iterations reached. So in order to do that, we just add the iteration so that you can be able to not get that error. So this is what we'll get, an output, and it will tell you it's a logistic regression that has been fitted. In this model now that we fit, we can extract a couple of elements. So the first one is the coefficient. So an array of the coefficients that we see that have been fitted, and this is what are these now? These are the log odds of the probabilities now that have been modeled, which is log of p over 1 minus p has been computed here. Then now we just want to extract them and put it in a data frame so that you can explain. So to do that, remember our array is just this. So we extract the coefficient, and then we also extract now the intercept, because we now want our coefficients. Of course, it will give us the list of the x variables. And then of course now we want the intercept also. Then we create this function that will now give us a data frame. So we want a data frame that will be calling summary data frame, and it will just take pd.data frame. What does it take? So our first column will be our feature, which will be the name of the x variable. So our first name is the feature, then xtrain.column. So we're extracting the column names. Then the coefficient is this coefficient element that we've created up here. Then the odds ratios, will just take the coefficient and then exponentiate. Remember, logistic regression has modeled the log odds. So we just want to convert the coefficient into odds ratios by exponentiating. Use the np.exp. So np, inputted numpy as np. Then for the intercept, we haven't extracted we need to kind of append as the last row on our data frame. So we just add here intercept pd.data frame, the feature. Of course, we need to create the intercept, the coefficient, then of course the odds ratio, just as we have done here. So we just create but one row, then of course we just concat at the lower bottom, then we ignore the index so that we don't have several indices for the variables, like feature here and again feature in the middle here. Then you can print your data set, your data frame. So what we have here is now the output of the logistic regression. How do we explain this? So we see we have our variable, then we have our coefficient, and then we have our odds ratios. So in explaining, I'll explain the odds ratios. I'll take a couple of two, then you can see a detailed explanation of the odds ratio in our previous video that we covered in this channel. So for gender, remember we had female being 0, then males being 1. So we are comparing from 0 to 1, a unit increase. So given an increase in gender, so between males and females, so being male is associated with an increase in odds of experiencing diabetes. So that means males are 1.23 times more likely of experiencing diabetes compared to females. Alternatively, you can say males are 23% more at risk of experiencing diabetes compared to males are 23% more likely compared to females based on this data. For the rest, it was a little bit. The rest does not offer significant values, because now even when we go and see the p-values of the rest, it wasn't significant. So it gives a small association with now from. Remember, 1 was African American. So when you African Americans to maybe Hispanic, we see that there is decrease in diabetes because we have coefficients less than 0. So that's what it means. But when you focus on a numeric variable such as age, we have it being 1.04. So it means that given a unit increase in age, we expect increase. You expect the risk of diabetes to increase by 1.04, or given a unit increase in age, the odds of having diabetes increases by 4.4%. So that is can last to what we see in literature and also what we see in real life. What about heart disease? So heart disease 0, heart disease 1. So those who have heart disease have 2 times the odds of having diabetes compared to those who don't have. So they have double the risk, and that's also true for the hypertension based on this data. So that's how we explain it. We have been able to explain. For a detailed explanation on how we covered this, you can see our description of our video on how do we interpret the odds ratios. I've also added this section so that you can see in detail. Alternatively, you can use the StatsModel. That's if you're coming from R and STATA and you just want to have a very beautiful this table output. So this is what it gives, used from the StatsModel package. So once you import statsmodel.api as SM, what you just need to do, you need to add the constant. So you need to add the constant at the independent variables. So by doing this now, adding the constants, then you come and fit the model. Now you're not fitting with the X string, but rather you're fitting with the X string underscore SM, the variables that you've created right now. Then you just print your result, and there you have it. So it's still the same. The coefficients, the odds ratios are almost the same. Lastly, we evaluate our model, and to do this now, we just use the diabetes model.predict. Remember, I mentioned that it has several elements. We've been able to extract the coefficient. Now we are predicting, but we give it new data. Then lastly, we print the confusion matrix. So this is the output we have. This is the true positive. This is the true negative. But you also see the false positive and the false negative. You can print the classification report also. Your classification report of the Y test versus the Y predicted. And it will give you this. So it gives you for the 0 and for the 1, diabetes no, diabetes 1. And then it gives you now the weighted average. So the precision, we can see the macro average and the weighted average of 96%, 96 and 96. So this is what we have as our metrics for precision, recall, and F1 score. Lastly, you can plot the curve, the AUC ROC curve. And to do this, we just import ROC curve and AUC curve from the sklearn.metrics. And then what we need, we just need to result the predict xtrain underscore SM. So we are using from StatsModel. And then we just, the ROC curve that we've imported, we give it now the xtrain and the Y probabilities. Then for this, it will be able to extract the false positive rate and the true positive rate. That's what we require. And then we just fit now, you compute the AUC score from the values. And then now we just fit the graph as we've done here. So you see, this is the curve based on the data, and we have AUC score of 0.96. Slightly higher than what we had in R, but this is what we have. So there we have it. We've been able to fit a logistic model in Python and also in R in this series. And this has been a very insightful series. The link to this video and to the files used in this video is found in the description of this video, and also you can find it in my GitHub repository. If you enjoyed this video, give it a thumbs up. I'm trying to just explain some of the machine learning techniques that we cover in data science class, and also what you may be able to implement in your day-to-day activities and also in your academic life. So the next video will be covering something else. We've been still in supervised machine learning. Ensure to subscribe so that you can get a notification for this. Thank you, and I'll see you in the next one.